This case study, it's the concept is all around smart farming and building an ecosystem around agriculture 4.0. As we know, there's a lot of lack of resources in the agriculture sector. The population growth is high, and the demand for food is also high. The consumption, obviously, is the same in terms of consumption for food. So we can see that there is always a high demand for the agricultural sector. And we all also have seen that this sector particularly has a little bit missed the area of innovation within this industry. What we'll be going into this presentation is to identify a little bit how the digitalization of the agricultural sector moved. As we can see, there was the phase one, which is more about the machine, integrating what the machine does in terms of data and performance. The next stage, which is phase two, is adding the layer of the data basically. So we are analyzing the machine plus taking in the data architecture. The next stage, which would be the hub monopoly, is then integrating all that data with the whole ecosystem. As also we can see from these slides, from the resource perspective and the market perspective, our case, our patent is more looking for into the enabling humans, how this patent really helps the human as a basic patent.
The patent we worked on describes a way to acquire, store images of fields in agriculture over time throughout the year. And the images that are acquired are analyzed to monitor the growth of the plants. So the use case related to this patent is to maximize the yield of the field. And indeed, with the data we gather, the farmer obtains the information that will help them find the optimal time to harvest. This can also be useful for mitigating the environmental harm, like, for example, the prevention of disease or insect outbursts. This will help the farmer make decisions about when to put additional manure too.
And if we ask ourselves, how can we expand this use case, we came up with this idea of georeferenced farming, actually. The first line is actually included in the patent that Valentin presented just a minute ago. So we capture very coarse spectral, multispectral images of the fields, average them, and then we determine optimal time to harvest. We think that if we improve the spectral data and amend that and include also airborne data, that we can create something like subfield details that would allow for managing actually the farming within the field, so that we can optimize, for example, the seeding. So create areas where we have higher degrees of seeding and lower degrees of seeding, use of fertilizers, where to fertilize and where not to fertilize, and where to guide our machines through. That would be the first expansion of the use case. And secondly, we can use in-field sensory, like for example cameras, to actually do single plant farming, so that we actually not farming a field, but a group of single plants. And within this in-field sensory, we can create a feedback loop that our effects that we did in the first case expansion of the case study, what effects do they have on the single plant? And of course, we can use this feedback loop to train an AI model and do artificial intelligence recommendation. And if we think of it one step further, we can actually do something like also a cross-generational approach on that one, that we store information from the 1 year and transfer it to the following years. For example, also take the fittest seeds from 1 year and use them to grow the seeds from the next year, and not for the entire field, but for certain areas of the field. So what we can do, create here something that we can call agile seed breeding. And what we see here, we have like left the unitary approach of one company and have like different linkages to other companies and other industries, for example, the seed industry, the machining industry, or the fertilizer industry.
So here is a presentation of generic IP strategies for conventional agriculture versus agriculture 4.0. So regarding the framework conditions in conventional agriculture, the whole product can be covered by limited number of patents. Before, the quest for higher yields meant larger machines, And nowadays, it's difficult for machines to grow further in terms of size, width, or age. So in agriculture 4.0, it's more and more important to introduce production-related know-how into process chains in such a way that efficiency can be increased further. Therefore, it's impossible to cover entire product with IP. And we can also have similar software or non-solution from other applications. Regarding IP strategic implications for conventional agriculture, they protect user-relevant features, and they also file strategic patents to block competitors with fast documentation and protection. Whereas for agriculture 4.0, they set proprietary rights standards, with standardized cross-system platform, which enables company to supply data from different sources in order to provide integrated solution with a form of IP right pool and IP holding organization. So that means we are on a value-added monopoly IP strategy for conventional agriculture and a monopoly for agriculture 4.0. Alex will now present you more deeply how this generic IP strategy applies to our use cases.
Thank you, Audrey, for that general introduction. So what does that mean for our specific case here for our imagery-based yield optimization? Well, as we don't know what exactly was the product that is underlying our use case or our patent imagery-based yield optimization, we can, for example, assume it's some kind of a software, a farm management system software. And our patent here enables this software. It adds a user benefit, it adds a value by adding imagery-based or image data to this farm management system to optimize the yield. So this can be seen as a typical value add monopoly. You have the pretty standard base of the software platform farm management system, and you add the customer benefit of the satellite image to detect the ideal point of harvest. And around that, you can build your sphere of exclusivity. So that means that the value-added monopoly aims at rather creating a closed ecosystem that protects customer benefits and value-added, and you build a sphere of exclusivity around this use case for the IP owner who can then exploit it. In the georeferenced farming platform and also data pool, of course, this looks a little bit different because we have way more complementers that are actually contributing to that whole system. So we have, for example, geodata providers that can also provide data on topography to create no-go areas for our machine. We have the fertilizer biocide manufacturers, the harvesting machine manufacturers who have to receive the data and act based on that. We have irrigation system manufacturers, maybe because we can set the irrigation based on the fields, on the crop conditions. We have governments and authorities, of course, who also have to interact, maybe give data to the data pool or interact with the irrigation system manufacturer to have all that water delivery, for example, regulated. And of course, we have our satellite or drone imagery providers who are also interfering here. So we have actually, as a hub, we have our georeferenced farming platform with the data pool that is attached to it in the databases, and we have the spokes around it, the complementers, so to say. And our hub monopoly in this case would use IP to set the standard that ensures the interoperability between the hub and the spokes. So we have a value creation network, so to say, that's defined by the IP standard setters, who would, in this case, hopefully be us as the developers and providers of the georeferenced farming platform. And we would let the others participate through an entry fee, so to say, a license. And now Maria Daniela and Anahita will explain how we can protect such an expanded use case through the right IP.
Thank you, Alex. So regarding the IP rights to protect this use case, we can use patents to protect interfaces and algorithms. Patents are the most relevant IP rights for this use case, relevant for exclusify the technology. We can also protect the algorithms by using trade secrets. Also, we can use copyrights to protect the source code of a software program. For instance, in the scanning or mapping technology built into the machine, and also to protect user interfaces. Also designs to protect user interfaces, trademarks to safeguard the brand. And we can also protect the database, including text, design, graphic, data, software, and images through copyrights. And Anaita will continue with the presentation. Thank you.
Thank you, Maria. For protecting the expanded use case, we can go beyond IP mechanisms. For example, using contracts for licensing and technology transferring, and also including secrecy clauses in those contracts. Certificates here can help standard setting and building the trust among manufacturers, suppliers, and all affiliates, potential affiliates in interoperability features of the expanded use case. By using the mechanism of plant breeders' rights, breeders who benefit from agile seed management and AI recommendations will be obliged to transfer all or a percentage of their rights in new varieties to the use case provider. Thank you.